So we'll be discussing screening and classification of solid particles, and then afterwards we'll be doing some problem solving on the topic. So again, screening is the separation of a mixture of various sizes of particles into two or more portions. And then as you screen, the resulting product or the resulting screened product is more uniform in size compared to the original mixture. As you can see in the picture in here, there's green, blue, and then orange and white particles, I think. Oh yeah. And then here, it's separated. So it involves passing a material over a surface provided with openings. So typically they are the screens. And then, as I have said, the type of screenings, dry and wet. The difference here is that here, there's natural moisture already. Whereas in here, water is added so that it can be treated. But sometimes each one has its own benefits, pros and cons. Of course, when you're dealing with a lot of powdery materials, it's very, very difficult to do dry screening. Sometimes you might want to have wet screening so that the powdery materials won't be dispersed in the air. So again, the importance, it prepares a product for sale or for subsequent operation. And sometimes, the sized material, each cut size might have a different value. It's analyzed either to control or gauge the effectiveness of another operation as well, just like crushing and grinding. And then, as I said, it determines the value of the product. So in screens, the different characteristics are the aperture. It's basically the clear space between the wires, and then the mesh number or mesh count, and then the pitch. The mesh, as I said, it's measured for every linear inch. So for every 1 inch, there are 5 holes or 5 openings. That is mesh number 5. The pitch is actually the opening area here plus 1 diameter or plus 2 radii. So in order to solve for the amount of open area, we can actually solve that percentage. How can we do that? We have a formula here. Here, percentage open area, but let's go to this first. As you can see all the time, di ba, the amount of open area naman kasi can be approximated kasi di ba, look, the total area in here is not just comprised of all open areas, di ba? It's comprised of materials, the wires, and the amount of area that is open for screening. So for the aperture size, I already gave you this formula last time. A is equal to L over N minus D. And then you can get the characteristics in the tables here. So just like here, for mesh number 4, the L is set as 1 linear inch, so that's 25.4 millimeters, divided by, since this is mesh 4, so that's divided by 4, minus, where did we get the 0.065? So the diameter of the wire, which is 0.065 inches, and then I converted that to millimeters. So this one, the aperture is in millimeters. For the mesh count or mesh number, it's the other way around naman. And then for open area, please be mindful of this formula. And then I won't go so much to this anymore. These are the types of weaves that's being used in screening. And then the common types of sieves, again, the important things to remember in here is that for Tyler standard sieves, it's on the fixed ratio of square root of 2, whereas the US standard sieves are by a 4th root of 2. And then for the methods of reporting, you know that if it's oversized or lays on top of the screen, typically you'll see the plus symbol. If it's undersized, it's usually negative. and then plus the pan, because the pan is the last. So again, here, this means it passes through 10 and then retained on mesh 20. And the methods of reporting screening analysis are differential, which is the easiest because here each fraction size is represented on the side beside the mesh sizes or beside the screens. Whereas if it's cumulative, you have to remember, if it's cumulative through the screen, everything will pass through mesh 4. That's why that's 100% passing. So here, when we focus on mesh number 8, we can see here that if it's 82%, 82% of the particles pass through mesh 8, or meaning that since mesh 8, looking at this one, mesh 8 has an opening of 2.362 millimeters, meaning the diameter of the particle, 82% of the particles have diameters less than 2.362 millimeters. And then another one is cumulative on the screen. So that means everything can be left on the pan, right? Because since everything passed through 4, nothing is left on 4. Only 7% is retained on 6, because look at this. Only 7%, because 7 grams out of 100 grams is retained on mesh 6. It's 7. So plus 11 is 18, can be retained on mesh 8, etc. So again, the ideal screens, this is important. The cut size. Screens are tasked to separate solid mixtures into two fractions, an overflow and underflow. So underflows are the ones underneath, and overflow, the one retained on top. For a given screen, the smallest particle in the overflow must be larger. That is for ideal screens. So whatever the diameter that separates them is what you call the cut diameter. However, for actual screens, the conditions on top does not really happen. Why? Because sometimes, even if this diameter of opening here is larger than those small particles, sometimes they don't pass through. And sometimes, even if this one is much bigger than the opening, due to its orientation, sometimes it passes through. So here are some situations of particles during screening. Particles sometimes can be too large, that it's easily retained. Sometimes it's too small, it passes easily. And sometimes it has a dimension of 1.1 times the diameter. That's why it causes blinding or clogging of the screens. You can see here. Okay, so let's go to some material balance on the screens. So you can see in here, the sample screen, and then let F be the feed, let R be the reject or the oversize, and then let U or P, sorry, let P be the product or the undersize in this case. So I can say here that, let's just say here, for the overall material balance, we can see here that F is equal to P plus R. And then, of course, if we want component balances, it's going to be F XF is equal to P XP plus R XR. I hope there are no problems in here. So it's important to know, like, that's why you're using screens. It's important to know how efficient the screens are. So this screen efficiency or effectiveness is the measure of success of a screen in separating materials A and B. Typically, guys, you'll notice that A is the, for us, typically A is the desired, and then B is the undesired or the reject. There, mass fraction, yeah. So ideally, A will be the underflow, so the desired product, because here the product is the desired. And then B is in the overflow or the reject. One measure of efficiency is the ratio of the undersized material A that is actually in the underflow to the amount of A entering the feed. So the amount of A in the product over the amount of A in the feed, that's the efficiency based on the undersize. Sometimes it can also be the efficiency based on how much was rejected. So the ratio of the oversized material B that is actually in the overflow to the amount of B entering the feed. So it's 1 minus. So reject 1 minus XR, feed 1 minus XF is the EB. Therefore, the overall efficiency, if you're asked, of the product is the product basically is the product of EA times EB. So that's the product of those two quantities. So let's just try. So if we have an overall material balance again of F is equal to product plus reject, and then let's just say the desired product would be F XF is equal to P XP plus R XR. What we do is let's say we replace R by F minus P. So I can say XF FXF plus so minus, sorry, minus F XR is P XP minus P XR. So if I factor out F and P, I can say that P over F, so P over F is XF minus XR all over XP minus XR. Can you follow? Also, I can say that the overall material balances can also be written as P is equal to F minus R, right? The OMB. So I'll use a different color for this. If otherwise, my OMB that I use is P is equal to F minus R. Therefore, using the same logic, I can say that F XF, and then instead of P, I'll use F minus R XP plus R XR. So FXF minus FXP is equal to RXR minus RXP. So if I want to solve for R over F, this is basically XF minus XP all over XR minus XP. So why am I writing this? Because look at this. It says here that the efficiency, total efficiency or overall efficiency is EA times EB. And then you have these. So if you have those, you can also say that based on that one there, I can say the overall efficiency is actually P. What's the P? over F. I can say that that is XP over XF multiplied by P over F, which is XF minus XR all over XP minus XR. And then the R over F is XF minus XP all over XR minus XP multiplied by 1 minus XR, 1 minus XF. So this one can also be equivalent to that one. Is it clear, guys? Using the overall material balances? Okay. Now, so capacity of the screen. So this refers to mass of a material that can be fed per unit time to a unit area of screen. So the units, be careful of this. Mass of feed divided by time multiplied by screen area, or mass of the feed time millimeter screen aperture times area. So let's do this. Calculate the clear opening and percentage open area of a mesh 6 screen, assuming a screen opening of 1/2 inch and a wire diameter of 1/8 inch. Calculate the percentage open area of the screen. So you're given this one. Let's try. So what is given to us? You know that it's mesh 6. So mesh 6 screen, it's this. Let's focus on this. So mesh 6 screen point. Let's write the given. For the mesh 6, these are what we need. The L is always 25.4. The D, or the diameter of the screen for mesh 0.036 inches. So let's just convert that. So what you're being asked to solve for is clear opening. So the clear opening is the aperture, right? And then percentage open area. So the aperture is the one that's being asked. We have a formula for aperture. As I said last time, aperture is basically L over N minus D. So here we can solve for this 25.4 over mesh 6. Therefore, this is 6 minus 0.036 multiplied by 25.4. Can you please answer this for me? What's your answer? 3.3189. And then what's the unit? It should be millimeter. So is it correct that the aperture is 3.32? A bit close, right? 3.32, that's a bit close. So let's solve for the percentage open area. So what's the formula? Let's write the formula first. Percentage open area is equal to A plus D squared. A over A plus D squared times 100 to make it percent. Can you please solve? What's this? So that's 3.3189 over plus 0.036, 25.4, square this, and then times 100. What's the answer? 61.47% open area. Now, assuming this screen opening of 1/2 inch and a wire diameter of 1/8 inch, calculate the percentage open area of the screen. So let's go to, this is for letter A. For letter B, you're given an aperture of 1/2 inch. And then a wire diameter of 1/8 of an inch. You're asked to solve for percentage open area. Can you help me calculate, please? Did you get 64%? So the answer is 64% open area. So I hope there's no problem with problem number 5. Let's try problem number 6. In here, let's read. 1 ton per hour of dolomite is produced by crushing and then screening through a 14 mesh screen. Using the screen analysis shown below, calculate A, the total load to the crusher, and B, the effectiveness of the screen. So important thing here is try to understand first the first sentence of the problem. 1 ton per hour of dolomite through a 14 mesh. So meaning if it's passing through a 14 mesh, it is important for us to separate them. It's important for us to separate this one. If it passes through a 14 mesh, let's separate this here. Why? Because everything on top here does not pass through 14 mesh. Everything at the bottom passes through the 14 mesh. Okay, so this one, we'll say that this one here, since this is the feed and that's percentage by weight, I can say that this is the X fraction of the feed. Am I correct? Because the fraction on top that does not go through 14 is not part of the feed. Am I correct? So here, you can see that this one is the product, the mass fraction, the product. And then here, this is the amount of reject. Because you're only considering, guys, those that pass through 14. Kasi ito, that's the oversize. Isn't it that the undersize, as we know, but this is the product, this is the reject, and this is the feed. Therefore, those are the compositions. So with this, can you help me? What is for here? What is XF, guys? This one, that's XP. This one's easy. That's XR. Can you give me what XF is? What's XF? Can you add those? 28.5, 8.6, 5.7, and 2.9. What's this much? 45.7. So I can see that this is 0.457. This one, when you add this is 100. So that's 1.0. This one, that's 0.24. Because this one, the total is 100. Am I correct? So when we write this, you can see that given, say it passes through a crusher, right? And then passed through the screen. So say this is your crusher. Passing through the crusher, and then that one is fed on to a screen. Some of it becomes the product, some of it is rejected. So this one is your F. This one is your initial F. Let's just say the total F. F total. But this one is the one that we try to solve because the orange F is the one that goes through the screens. So again, this one is the crusher. That one here is the 14 mesh screen. So if this is F, you have an XF. If this is R, you have an XR. If this is P, you have an XP, right? So what's required? Total load to the crusher, so meaning the F that goes into the crusher and the effectiveness of the screen. So required, letter A, what's the load to the crusher and the effectiveness of the screen. So how do we solve this? First, of course, is your overall material balances. Overall material balances, F is equal to P plus R, and then component balances. You know that that's FXF is equal to P XP plus R XR. So with this, you are given, what else is given? Are we given any amount? 1 ton per hour is produced by crushing and then screening. So 1 ton per hour of dolomite. Okay, so that means I have a question, guys. 1 ton per hour is produced. Is that letter F or letter P? Read the problem carefully. The 1 ton per hour of dolomite. Should that be letter F or should that be letter P? Try understanding the problem carefully. Just try, just try. What do you think is the 1 ton per hour? Sa product. Tama. Bakit hindi siya pwedeng feed? Because I look at this. 1 ton per hour of dolomite is produced by crushing and then screening. So after you crush and after you screened, that's when you have the product. So here, baka pwede natin lagay sa ilalim. Basis. 1 ton per hour. P. Ano yung 1 ton? I can just say 2,000 pounds per hour. So, kung 1 hour ang basis natin, I can just say here, F, here. F is 2,000 plus R. So, I can say in here na F times X of F, you know that that's 0.457. And then P is 2,000. The X of the product is 1.0. And then the amount of reject, you don't know. But then this one is 0.24. So guys, you have 2 equations, 2 unknowns. Can you please help me solve F and R? Equation 1, equation 2. What is F and R? What's the answer for F, guys? It is 7,004. I got the same. 7,004.61 pounds. The other one is 5,004.61 pounds. So Since you're just asked to solve for F, so on a per hour basis, 7,004.61 pounds per hour. Now, let's solve for the efficiency. How do we solve for the efficiency? You're asked to solve for E. You have a lot of different formulas for E. You can say here, there, the one at the bottom, if you want, okay? Or if you want, you can use this EA and then EB and then multiply the final answers. So let's try. If it's XP over XF minus XR, XP minus XR, XF XP, and then 1 minus XR all over there. XR XP 1 minus XF. Can you please plug in, guys? Take note of the XP, XR, and XF. What's your answer? What's your XF? 0.457. XR is 0.24. So 0.457 minus 1. 1 minus 0.24 all over 0.457. 1 minus 0.24. And then XR 0.24 minus 1. 1 minus 0.457. So this one is 0.6248, or it is 62.48% efficient. Okay? So this is your final answer. It's quite clear. What's important, guys, that I need to remind you is this. Me, for easier understanding, what I do is I cut it. I draw a line so that I know, everything that passes through the 14 mesh is part of what I am dealing with. Everything that's not passing through it, I don't care about them. Okay? Problem number 7. Limestone is crushed by 6 units operating in parallel and the product separated by 6 35 mesh screen also in parallel into 2 fractions. The effective dimensions of each screen is 6 feet by 20 feet. The common undersize from the screen comes out at a rate of 50 tons per hour. Assuming that there are no losses, determine the efficiency of the screening operation and determine the capacity of each screen in pounds for every 24-hour per square foot. Take note, separated by 6 35 mesh screens. So 35 mesh screens, I should know that I'd be cutting it at this portion because it's separated by the 35 mesh. Okay? So can you help me solve this? What is your x of f? What's your x sub r? And what's your x sub b? Can you help me, please? X sub r, it's easy, 0.175. What's x sub f? 0.45. What about the x sub b, please? 0.65. Hang on, guys, wait lang. Okay, so in here, let's write the given. You have 6 screens, 6 parallel screens. So the feed goes to a set of screens. So let's just call this a set of 6 screens. And then you'll get your product and your rejects. So let's just say, let's just place the rejects on the side, the products at the bottom. So your 6 screens here. So all right, what else is given? You know that the product comes out at a rate of 50 tons per hour. So here, 50 tons per hour. And then the 6 screens have dimensions of 6 feet by 20 feet. So 35 mesh that has dimensions of 6 feet by 20 feet. What's being required? Letter A, I think it's the efficiency, the total efficiency of the operation. And letter B, capacity of each screen. So capacity of each screen. So let's solve. So let's just use a basis of 1 hour. So for the OMB, it's all the time F is equal to P plus R. So I can say F is 50 plus R. And then the desired and undesired. So FXF is equal to P XP plus R XR. So F and then the XF is 0.45. The P, the product is 50. XP is 0.17, no, 0.65. And then R, and then 0.175. So with this, equation 1 and 2, you can already solve for F and R. Can you please help me solve for F and R? F is 86.36. What's the units? Tons per hour. And then reject is 36.36 tons per hour. Okay, so this is basically just using the OMB, but we haven't answered the efficiency yet. So in order to answer the efficiency, we can use all the different formulas in there. We can just basically say, but this is, as I have said earlier, the recovery multiplied by the rejection. So for the recovery, it's PXP over FXF multiplied by the rejection, which is 1 minus P, 1 minus XP, F1 minus XF. You might say, where did I get this? Isn't it that's one of the formulas is this? Look, this one, and then this is the reject. So I can say that the R is actually, so here, it's basically parang 1 minus lang siya. 1 minus the recovery is the rejection, right? So what did you get here? Were you able to get, guys, 52% or 52.82%? How many got that? Were you able to get that? Nicole was able to get that. Are you able to get that, guys? So this is 52.82% recovery or efficiency, sorry. That one is your answer for letter A. Are you able to get this? Okay. Now, we were able to answer F and R. But the thing is, we haven't answered the capacity of each screen. I have a question. I have an F, I have an R here. Which one should I be using to answer the capacity of the screen? The feed or the recovery or the reject, sorry. Should I be considering F or reject in terms of the capacity of the screen? Should be the feed kasi the feed is the one that goes to the screens. So here, in solving letter B, we know that the F I was able to solve for is 86.36 tons per hour. Right? Therefore, the capacity of the screen, how much can the screen handle, is a mass flow rate. Because the capacity that's being asked to solve for is pounds per 24-hour per square foot. So here, pounds per square foot per 24 hours. That's the units. I have here an 86.36 tons per hour. So what I need to do is I just multiply this by, for every 1 ton, I would just ask you to use 2,000 pounds. Okay, we're done with the pounds per hour. Now I need the square foot. You know that each screen is 20 by 6. So 26 screens by 20 by 6. Right? So we were able to answer per screen already. Individual screen and then square foot already. The thing is 24 hours. This is on a per hour basis. Right? So what I do is, can you solve this first for me? Because this is on a per hour, not on a per 24 hours. So what I do is, I can multiply this by 24 hours. 24 hours. Some of you might ask, why sir, multiplying by 24 over 24, isn't it equal to 1? I have a point. Because look at this. The units that I have at the moment is pounds per square feet hours because of the hours at the bottom. But what's being asked is for every 24 hours. So for me, if I place 24 hours at the bottom, I just multiply by 24 hours on top. Right? So, like this. So can you please solve this for me? 86.36 times 2,000 divided by 6 divided by 20 divided by 6. What will this give me? 239.89. So 239.89. But then that's the units. What I need is pound per square foot 24 hours. Guys, multiply the answer by 24 hours. What would be the answer? If you multiply this by 24 hours, 5,000 757.33. This is on a per screen basis already because I divided by 6 screens. But if I did not divide by 6 screens, hindi siya per screen basis. So this is the capacity per screen for every 24-hour operation. Can you follow, guys? All right.